Hi, my name is Friderike Irmen, and I am very pleased to have been awarded the prize for my dissertation from the Berliner Gesellschaft für Psychiatrie and Neurologie. And here I would like to briefly present myself and my research. The title of my dissertation was Understanding the Impact of Subthalamic Deep Brain Stimulation on Cognitive and Affective Processing. Just quickly, who am I? I am a psychologist and have studied clinical neuroscience as my master's degree and worked in research in Denmark for a while before starting my PhD here at the Charité at the Movement Disorders and Neuromodulation Unit with Professor Andrea Kühn. I was supported by the Berlin School of Mind and Brain, and I'm still currently working as a postdoc at the Neuromodulation Unit, now in a project where I'm collaborating with Professor Henrik Walter and Professor Fred Hamka. In my dissertation, I was specifically looking at deep brain stimulation impact on cognitive and affective symptoms in Parkinson's disease. The main target for deep brain stimulation in Parkinson's disease is the subthalamic nucleus. And what's interesting about this region in the basal ganglia is that it receives not only input from motor regions, here in red, but also from associative regions like the dorsolateral prefrontal cortex and so-called limbic regions like the anterior cingulate or the orbitofrontal cortex. So there's a lot of information from different brain areas that is sort of converging here in this region, and then deep brain stimulation is thought to interfere with that. The basal ganglia are per se disturbed in their function in Parkinson's disease, so the lack of dopamine in Parkinson's disease interferes with the control of movements, emotions, behaviors and thoughts. And this is also what one has to consider when doing research with deep brain stimulation, because there is a disturbed baseline already. Now, the research questions that I was mainly interested in were how DBS interferes with very specific cognitive affective processes, and I was interested in emotion processing and risk processing, and also depression symptoms. And then how do the observed behavioral changes that we see in these patients relate to electrode placement and connectivity? So the first study I conducted was looking at emotional conflict processing. Here, the motivation for the study came from the fact that DBS impairs affective processing and response slowing in situations where there's high conflict, so high and high arbitrary, The first study I conducted looked at SDN, DBS and emotional conflict processing. Here the motivation for this study came from the fact that DBS and the SDN impairs affective processing. That's what we see in patients with Parkinson's disease, and also response slowing in situations with high conflict, so where response inhibition is required. And I applied an emotional Stroop paradigm where we compared Parkinson's patients on and off SDN DBS with healthy controls. So the patients with Parkinson's disease conducted the emotional Stroop paradigm with the device switched on and with the DBS device switched off. And then we also simulated the behavioral data using an adapted version of the renowned Stroop model, so a computational model. The results here were that Parkinson's disease patients were unable to slow down their responses in conflict trials. So if the face emotion did not match the written word, they were supposed to slow down their reaction times like healthy controls, but they didn't. So that sort of fits the idea that deep brain stimulation suppresses this ability to slow down responses in the face of conflict. And then we also saw a strong valence bias in the responses of Parkinson's disease patients of the brain stimulation. So here there was a strong negativity bias. They slowed down a lot for negative stimuli and not so much for positive stimuli. So that suggests that there's an attentional bias in these patients. And with the computational model we used, we could show that the disrupted response adaptation on DBS was due to an increased noise level in the SDN. So to conclude, in this study, I could show that SDN-DBS disrupts emotional conflict processing in Parkinson's patients. The next study looked at risk attitude and judgment of reward and the impact of SDN-DBS on this. And here there was a previous study by my former group in Copenhagen who looked at SDN activity during a task, and they found that SDN activity was changed in this specific task based on escalating risk in a task. And this task was a dice game. Here, the patients had to were sitting in front of a computer playing this game, and they had to continuously decide whether to keep rolling a dice. And every time they would roll a dice, they would earn the money of. They would earn the virtual money of equal to the pips on the dice, and at each time they would roll the dice, the sum would increase. And at some point they had to decide to stop and bank the current amount. And if they would not stop or keep going on for too long or just be unlucky, they would roll a 1, and then they would lose the lot in the round win. So in this sequential decision-making task, they had to continuously decide whether to continue to roll the dice to earn more money or to stop and bank the current amount. And the performance of 17 Parkinson's patients, again with the device, DBS device switched on or off, was compared to 17 healthy controls. And then I also localized the electrodes, the DBS electrodes in the brain using the Lead DBS software developed by Andreas Horn from our group. And the results of this study were that risk attitude was actually different between the groups. And here we could see that off the brain stimulation, Parkinson's patients were very risk averse and much more risk averse also than healthy controls. And DBS sort of normalized this risk aversion to a healthy level, so that Parkinson's patients would make an equal gain in the end in this game than healthy controls. And interestingly, when we looked at the placement of the electrodes, this normalization effect of the brain stimulation was dependent on electrode placement. So if the electrode placement was good and targeted the motor SDN as intended, then risk attitude would normalize. So patients would make more healthy choices. And if the electrode placement was suboptimal, so would more target the associative part of the SDN, then there would be a lesser change in the risk attitude. So this was the second study, and finally the third study that I conducted for my thesis was looking at whether electrode position and associated connectivity could explain postoperative changes in depressive symptoms. So we see symptom changes in the depression scores in Parkinson's patients who get DBS devices, and these can also be long-term, and usually they're reported to improve in their depressive symptoms with deep brain stimulation, but there are some mixed results here. And I had the data from DBS scores before and 6 to 12 months after DBS surgery of 116 patients from 3 different DBS centers, Cologne, Berlin and Brisbane. And then I reconstructed the electrode position and estimated the structural connectivity of these patients. And these are the electrode positions. what I could find is that there is a very robust structural connectivity profile associated with the depressive symptom change. Namely, that if the electrodes were stimulating fibers that were connected to the left prefrontal cortex, and the hotspot was the left dorsolateral prefrontal cortex, the depression symptoms would get worse. So this is sort of the first study that could show that there's a consistent structural connectivity profile predictive for the change in depressive symptoms. And interestingly, as some of you might know, the left dorsolateral prefrontal cortex is also the clinical target for rTMS and major depression. And there's many studies that show that the left dorsolateral prefrontal cortex in depression is hypoactive. So it seems that this left lateralized impact of STN-DBS on prefrontal regions makes sense, and that it explains the worsening of depressive symptoms in patients with Parkinson's disease who get DBS. Yeah. In summary, I can show that the cognitive and affective profile of Parkinson's disease includes an attentional bias towards negative information, as I could show in the emotional Stroop task, and also that they are more risk-averse than healthy controls, as I could show in the second study, and the depressive symptoms we already know about. And STN-DBS improved these Parkinson's-specific biases, for example, by improving the risk attitude, as in study 2, but it can also lead to cognitive disinhibition, and that I could show in the first study in the emotional Stroop task. And importantly, electrode placement plays a very big role, and the associated structural connectivity, of course, as well. So this determines the outcome, and depending on where the electrode is placed, different fibers are stimulated, and then this can determine or predict a change in depressive symptoms. And of course, this research, in my opinion, has high clinical relevance because we're aiming to control non-motor adverse events in this patient group and also tailor DBS therapy, also now with the development of adaptive stimulation techniques. Yeah, thank you again for awarding me with this prize, and I would like to thank especially the supervisors of my dissertation, Andrea Kühne and Hauke Hekerin, but also all the other people who have supported and mentored me, and my entire group at the Charité Movement Disorders and Neuromodulation Unit. Thank you very much.